So lecture number 8, Introduction to Game Theory. I'll talk about what game theory is in a second, but as most of you saw, and thank you for doing this, I played a little game via an announcement called Choosing Numbers. Who has seen this game before in the past? Maybe I saw, there's a couple of half hands up, so a couple of you have half seen this before. So everyone in the class secretly chose a number between 1 and 100. And what we did was, I'm going to calculate the average number chosen for everyone in class. So for example, if everyone chose 50, the average is 50. If everyone chose 100, the average is 100. And the winner would be the person who chose closest to 2/3 of the average number that was chosen. So it's a little bit of a tricky game. I'm not sure how long you thought about it, but here are the results for that game. So I made up this little histogram. And so as of about an hour ago when I made this, there were 40 responses, which is awesome. So that's the most responses I've ever gotten. That's about half of all the students enrolled in the course. Thank you for that. So the average was 31.6, and 2/3 of the average rounded to the nearest integer was 21. So it was about 21.05 or something like that. And that means that, so there were no 21s chosen, but there was a 20 chosen and two 22s chosen. So if you are one of those 3 people, just put your hand up real quick. Anyone? Nobody? Nobody? Oh, we got one. Okay, which one did you choose? So what was your reasoning for choosing 20? But was there any like, okay, if I choose this and they choose this, or did you just say I like 20? Okay, so I've had people say, I chose my birthday, I chose the day of the month, or whatever. So this was the game, and we'll talk about a little bit of game theory, and then what we'll do about halfway through the lecture is I'll come back to this game and we'll do a little bit of analysis for the game. So just keep in mind that that's the game, and if you didn't see the post on D2L, this game is quite interesting. So what is game theory? It doesn't have to do with Super Mario Brothers. It could, but in general, it doesn't. And what it is really, it's a mathematical model for decision making. Has anyone here done any game theory in any courses before? Okay, so I know you're in math, so the math people have probably done a little bit of game theory. And so essentially, it's an analysis of strategic actions in scenarios which can be defined as games. And what we'll find in life is that you can pretty much define anything as a game if you want to. We talked about that a little bit already. It has a lot of uses in the social sciences, computer sciences, economics, everyday life. And in fact, the place where I would say game theory is probably used the most is in economics. It came out of economics. And so the interesting thing is that nobody actually teaches us how to make decisions, right? People in classes and in school and your parents, they probably give you a bunch of knowledge, or they tell you what to do, like don't hang out with that person, or you shouldn't date that person, or you should have this type of job. But do they say why, or like why you should make those type of decisions? And so game theory is great because it's one of the only things I've ever learned about that's really helped to make real life decisions. So let's look at some contrived games. So I've made up some examples of games. Actually, I've borrowed them from other people who have taught similar classes in the past, but I couldn't find the originator of all this information to actually give credit to. But any numbers that you see in this game are just completely made up, okay? They may or may not have anything to do with real-world analogies. I'm just making up numbers so that we can do some math with those numbers. So here's the grades game. 2 people secretly and simultaneously make a choice with a defined outcome. So you and some unknown partner are going to make a choice. The choice is between choosing alpha or beta. And alpha and beta have absolutely no bearing to any real life decision. They're just 2 symbols that I could assign to choices. Okay, so alpha's not better than beta or anything like that. They're just letters. And here's what happens. If you choose alpha and they choose alpha, you get a B-. Okay, so this is some crazy game that will decide your grade in the course. If you choose alpha and they choose beta, you're going to get an A. If you choose beta and they choose alpha, you're going to get a C. And if you choose beta and they choose beta, you're going to get a B+. So So just think about this for a second, and then someone put up your hand and say, would you choose alpha or beta? At this point, there is literally no wrong answer. I just want to hear the reasoning that one or two people have. So behind the hat. Yeah.
Alpha.
Why would you choose alpha?
People would be scared to choose because they also, reverse psychology.
Okay, so you think there's some sort of psychology going on in the back there?
Yes, choose alpha.
Okay, so you have a probability of getting the highest outcome. So that's like a sort of maybe some people would want the best outcome. Some people might want like not the worst outcome or some sort of medium outcome. Different reasoning in the hat. Yep.
Over the course of many instances, you'll always average out to have a higher grade with alpha.
So we're talking about averages and stuff like this. Anyone? Yep, over on the side.
I would choose beta because I see that if they choose beta as well, then it's B plus.
Okay.
Yeah, if I choose alpha and they choose alpha, then it's B minus.
Yep.
That's
Okay, so I got. Did you have one you really wanted a different reasoning, or you just?
same reason. I chose alpha like that.
Okay. So averages, highest, stuff like that. Let's do a little bit more mathematical analysis on a problem like this. And something I'm going to do when you're talking about mathematics is that one of the reasons why this choice is a little bit difficult and why people make different choices is just first and foremost because the information is kind of hard to parse, right? If it's in this like big long string or description and you're trying to remember, okay, I have alpha, they have alpha, it's B minus and it's C and all this kind of stuff, it's literally just hard to parse that information. And so maybe the first lesson of game theory is whenever you're confronted with a choice like this or an English description of a problem, try and put it into a way that you can more easily parse the answer, first of all. So what we're going to do is we're going to phrase this as a matrix. Okay, so this is an outcome matrix. So that's why this is called matrix games. So these are games that we can put in matrices. So what I've done here, so alpha, alpha, B minus for me, alpha, beta, A for me, beta, alpha, C for me, beta, beta, B plus for me. I'm just going to put that into this matrix. So over here, I have my decisions on the left, and up here, I have my partner's decisions on the top. And here is the outcome if we both make these choices, right? So if I choose alpha, they choose alpha, B minus. If I choose alpha, they choose beta, A. If I choose beta, they choose alpha, C. And if I choose beta and they choose beta, B plus, right? So you can instantly see how much easier it is to parse this information. And so you can look at it all and you can say, okay, even my eyes don't have to move as much, right, to parse this information. So it's a good idea to write things down as compactly and efficiently as you can to help you really understand the problem a bit more. So now what we're going to do is we're going to do the same thing, but we're going to write it from the point of view of the partner, right? So this would be my partner's outcome, which is essentially just like the transpose of this matrix, right? Because we both get the same outcomes if we play the games from opposite points of view. So here, the primary diagonal would be the same, but where I was going to get a C before, they would get an A, and if I was going to get an A, they would get a C, all right? But now we have these two matrices, which is a little bit tough to parse, right? It's easier than the problem description. So what we're going to do is we're going to combine these into one final matrix, which shows the outcomes for everybody. And this is the final outcome matrix for this matrix game. And so what we have here is that the first element of each cell is this person's outcome, and the second element of the cell is this person's outcome, okay? So if I choose alpha and the partner chooses alpha, we both get a B minus. If we both choose beta, we both get a B plus. If I choose beta and they choose alpha, I get a C, they get an A, and if I choose alpha, they choose beta, I get an A, and they get a C, okay? So, after having seen this, anyone who had raised their hand initially, would you change your answer based on the information? Okay, I got some yeses and some nos, so why would you change it?
Just the statistics look better for alpha.
Statistics in what way?
The average.
Okay, so so the response there, just for the microphone, is that if we maybe take all the possible outcomes and sum them and average them, that would be the highest or something like this. Okay, that's perfectly logical outcomes. But let's go a little bit deeper. So we have actions, strategies, and outcomes. A strategy here is an assignment of a choice to both players. So if I choose alpha and you choose beta, that is called a strategy. And the outcomes are the things in the matrix. But this isn't quite a fully formed game. Can anyone venture a guess at what we might be missing from this outcome matrix? Yes?
If the reward is just very skewed on one outcome, so it's not necessarily fair to pick either alpha or beta. It's just skewed.
Sure. But what I'm looking for is, like, when we play a game, right, typically there's like a score or a win or a loss or something like this. And so whether or not I get a B or an A, it's like, which of those do I really favor, right? If we're going to do mathematics, we can't do mathematics on letter grades, right? So what we're going to do, the thing that we're missing here, is called a payoff. So what is our objective or our goal in the game? And so the interesting thing is that game theory can't help you decide the relationship between outcomes and payoffs. You have to decide that. But if you do have payoffs, game theory can decide how you want to maximize those payoffs. So for example, someone in the class might be greedy. All we care about is our grade. And so I am going to assign a higher numerical value to me getting a higher grade. That's it. That's all I care about. I don't care what the other person gets. This is my grade. It's my future. And that's fine, right? Like, that's a fine thing to do. Maybe someone else, maybe the person that got chosen was a family member or your friend in the class. And so you would also assign some value to the grade that they got, right? So here's an example. So a payoff is assigning numerical value to some described outcome. So how much do I like the outcome? And the more I desire that outcome, the higher the payoff, essentially. So an example payoff, let's just say, imagine one of the players is greedy and assigns higher payoffs if they do better than their partner. So for example, let's say I see we're both going to get a B minus. If we both get a B minus, that's kind of neutral, right? I'm not happy about it. I'm not sad. It's not great, not terrible, if you've watched the Chernobyl series, right? Not great, not terrible. But if I get an A and you get a C, that's great for me. So I'm going to assign like a higher value, maybe 3, to that outcome. Now, again, what I'm saying here, these numbers are just chosen to have some sort of real world analogy, but whatever the values are, aren't super important. What matters here is the algorithm that we're going to show for making decisions. So what we do is we take this matrix here and we turn it into this outcome matrix. Okay, so for example, a B minus and a B minus, that's kind of neutral. A B plus, that's a little bit better, so maybe we both care about that 1. If I get a C, then that's bad for me, so I'm going to say that's a -1. If I get an A, that's a 3. Okay, so let's assume that both of these players have the same payoffs for those outcomes. So these numbers are called utility. And utility just means like, how much do I want something? The utility of something is a good thing. If the number's higher, that's better. And players should attempt to maximize their utility, right? Because I have already gone through whatever process it is of assigning values. And so I want to maximize that value, obviously. If I could get a 5 instead of a 2, I always want to get that 5. And whatever you did to get those numbers, you are trusting that to be the correct thing. And so for example here, I just said these, so B minus goes to a 0, A and C goes to a 3. So this player, you know, maybe they're a little bit greedy or something, if you want to put it that way. So what should you do in this case, right? So before there was no wrong answer because all of you were assigning different payoffs to this matrix. Some were caring about the highest grade, some were caring about the average grade, and so up until now, there was no wrong answer. But on an exam, once you have payoffs, there will be a wrong answer, right? So what should you do? Well, Sun Tzu in The Art of War says, consider all choices, right? You must know your enemy, become your enemy to overcome your enemy. But this isn't necessarily enemies. So let's have a look at all the possible choices. And instead of first looking at all of our choices, we're going to do this a little bit backwards. We're going to first consider everything that the other person could do. Okay? So, let's say that our partner chooses alpha. So that's one possible thing that could happen. If they choose alpha, if you choose alpha, you're getting a 0. If you choose beta, you're getting a -1. Okay? So that's what will happen if they choose alpha. And then look at your choices. If they choose beta, if you choose alpha, you get a 3. If you choose beta, you get a 1. So, no matter what they do, alpha is always the best choice. Okay? And this isn't some tricky thing where maybe 1 out of 100 times they'll choose the other thing or whatever. No, this is literal just mathematics. No matter what they do, you should choose alpha because it's literally always better, right? So hopefully now, given this matrix of payoffs, you can make that choice. And so in this case, since alpha is always better than beta, beta is called a dominated strategy. Okay, and we talk about domination, strategy domination, from the point of view of, is there a strategy that something else always does better than it? Okay? So we say that a strategy, alpha, strictly dominates a strategy, beta, if my payoff from alpha is strictly greater than that of beta, no matter what others do. Okay? And this strict domination means strictly greater. So it's always better to do this thing. There is no ambiguity. No matter what they choose, this is always the best choice. And so the first rule of game theory is that if you can identify a dominated strategy, never play the dominated strategy. Okay? So back here, we identified that beta was a dominated strategy. We are never going to play a dominated strategy, so the only other choice is alpha, so we should play alpha if we are a rational agent. So the strategy that dominates it is better in every possible case, no matter what. Okay? Now, just keep in mind, because this is a little bit confusing, we are not saying that there is a dominating strategy that's always best. Because we could have 30 actions, right? We're not talking about the one action that's the best. We're just talking about identifying a strategy that another strategy is always better than. So, let's have a look at this common game. Hands up if you've heard of the prisoner's dilemma before. I'm sure a bunch of you have. Yep. So, here's the prisoner's dilemma. And now, keep in mind, this is not meant to be any sort of discussion of like our criminal justice system or anything like that. This is just a thought experiment in which we assign values to outcomes. So there's 2 prisoners in 2 separate cells, and they've both gotten caught at a crime scene or something, right? Let's pretend that they were in cahoots. They were partners for some crime, and the cops, yes, they found them there, but they couldn't just be passersby. They don't have enough evidence to just lock them up, okay? So they put them in 2 separate cells. They're not going to question them at the same time. The first thing you do is you separate the people, and you ask them questions independently. So the guards or the police officers are going to ask the prisoners to rat the other one out, meaning that I'm going to tell on that person. So they're like, listen, they're playing the good cop, bad cop thing. So they say, all you got to do is tell on Joe. Just say that Joe did it, right? And you'll get all these benefits. And the other one is saying, Joe, just say that Dave did it, right? And so what's the outcome of this situation? So let's just make up some outcome that's sort of similar to what might actually happen, but probably isn't, right? So if neither of them tell on each other, they have enough evidence to lock them up, but just only for a little while, right? Not the full sentence. So if neither of them say anything, they both go to jail for a year. Because yes, they were at the crime scene, but they don't have all the evidence. They don't have the confession. If both of them tell on each other, then they have the evidence. So they can lock them up for longer, but maybe they give them a little bit of leniency for having actually told the truth, right? So they have the evidence, so they're both going to go to jail for 2 years. But if one of them tells on the other, and the other one doesn't tell, then the teller goes free, and the other one goes to jail for 5 years. Because they pin the whole crime on the one guy, right? So this is the outcome here. Now remember, these are outcomes. We cannot apply any game theory to outcomes. What do we have to apply game theory to? Payoffs, right? So we need to turn these things into numbers. And what I'm going to do is do something that probably is not like the real life case, but I'm just going to assign -1 to every year spent in jail, right? Now, it's probably the case that like 2 years in jail is not necessarily double the punishment of 1 year in jail, but we're just assuming linearity for all of these things. So here is the payoff matrix for this game. If both people tell, they both go to jail for 2 years, so they both get a -2. If both people stay silent, then they both get a -1. If one person tells and the other person stays silent, the person who told goes free, so it's 0 years in jail, and the person who stayed silent gets a -5. All right, and it's just the opposite for down here. So let's have a look. What would you do in this situation? Let's apply the same algorithm. So we'll look at the other person. Let's pretend we are player 1 for right now, or prisoner number 1. And prisoner number 2, okay, let's say that prisoner number 2 is going to tell. If prisoner number 2 tells, if we tell, we get -2. If we stay silent, we get -5. Okay? So let's look at the other thing. What if they stay silent? If prisoner 2 stays silent, we get a 0 if we tell. We get a -1 if we stay silent. Okay, so in this case of the prisoner's dilemma, with these payoffs, ratting out the other person, so telling on them strictly dominates, not ratting them out. Now, you might be thinking in your head, yeah, but it's not always better to tell. Maybe if we both stay silent, when we get out of jail, our boss is going to give us $1 million or something, right? If that's the case, then you have to factor those into the payoffs, not into the algorithmic decision-making choice. So if there's some other reason I care about that person, they've got a baby, maybe I'd go to jail for them for a year if they got free. All of that has to go into the numbers, right? And then we use game theory to choose it. So with these payoffs, telling strictly dominates not telling. There was this show, the Split or Steal game show, and this was one of the most hilariously dumb shows that was ever on television. And so, in this game show, 2 contestants, they have golden balls in front of them. One of the golden balls contains the word split, and one of them contains the word steal. And so, what they do is they sit 2 people down in front of each other for 10 or 20 minutes while they cry about how their dog has cancer, or their grandmother is in the hospital, why they need the money. Oh, I promise you, if I win, I'm gonna split the money with you, or I'll give you 25%, or oh, my husband is it. It's a drama show that in the end, all that happens is you choose one of the balls and then you both go bloop. Okay, at the end, you reveal what you chose. If they both chose split, then they each get half. Let's say it's $50,000 or $100,000. It's something that's like a lot of money, right? If they both steal, they both get nothing. If one splits and one steals, then the stealer gets everything, right? So, what game is this? This is the prisoner's dilemma. And the vast majority of the people on this show had never heard of the prisoner's dilemma, obviously, right? So, this particular one where I have the GIF down here, the reason this guy looks like that is because this guy is sitting like across from this beautiful woman, and she's like, oh, you know, like you're a nice guy. He like falls in love with her over the course of 15 minutes, of course, right? And she convinces him, we both have, you know, pretty decent lives. Neither of us is gonna like, you know, get too much out of this. So let's just split and we'll go home. And you know, all this stuff. And anyway, he falls for it. He chooses split. She chooses steal. She gets all the money. And the other rule of the show is that nothing that was said during the conversation is legally binding, right? You can say, I swear on my grandmother's grave, I'll do all this, but that's part of the game. Okay, so that's pretty funny. You can look that clip up on YouTube, but that still wasn't the best episode. I'll tell you about the best episode in a second. But let's have a look at this, right? What is the best choice here? So if we assign linear payoffs to this money, here's the matrix that we get. If we both split, we both get half. If we both steal, we both get nothing. Otherwise, split steal, the stealer gets everything. So in this case, okay, let's have a look. If they split, if we split, we get half. If we steal, we get 1. If they steal, however, we get 0 for both of our choices. Okay, so in this case, stealing weakly dominates splitting, meaning that I can do as good or better. I'm not always better, but in this case, I'm going to do as well. So I can't say I always do strictly better, but I'm always going to do at least as well by choosing steal in this case. So the game creates drama by allowing players to talk to each other, etc., to try and make a deal. That's an interesting show. You can go look up a clip. But this was my favorite one. So I've linked the YouTube clip in the slides because I think it's hilarious. These two people sit down. The guy on the left starts, you know, the regular spiel like, oh, I got these bills and whatever. Let's make a deal or let's both split. The guy on the right, who is obviously a mathematician, just says, I hear what you're saying, but here's what's going to happen. No matter what you choose, I'm going to choose steal. So if you choose steal, we both get nothing. Fine, I'll go home, I'm all right. But if you choose split, and I get all the money, I'll give you half. That's it. Nothing you can say can change my mind. And the other guy's, no, wait a minute, let's talk about this. He's like, nope, I'm choosing steal. Right? As you would if you knew anything about this game. But the other guy doesn't want to go home with nothing. So he's like, this mother, you know. He just has to choose split and hope the guy gives him half the money. And so anyway, I won't spoil what happens. But go watch the clip because it's hilarious. Okay, hand up if you want me to spoil it. Okay, more than half. So anyway, in the end, that guy like begrudgingly chooses split, but it turns out this guy chose split as well. Right? So he just takes it home. But I think the next season the show was canceled because I think he just showed how dumb the show is because someone can just say that and lock the other person in. Okay. So I thought that show was funny, but also dumb. So an important note, decision-making using game theories assumes the payoff matrix is accurate for your utility. So getting $1 million might not have double the value of getting 500,000. You might not care as much about beating the opponent or getting a higher payoff, right? So direct translation from real life outcomes into numerical payoffs is actually quite difficult. So game theory doesn't solve the whole problem for you, it just solves the algorithmic problem for you. And so here, where we talked about before, these grades that we got, these are the grades obtained by both players in the grades game. What might a sample payoff matrix look like for different types of players? So what do I mean by that? Well, here, me and my partner, when I made the last payoff matrix, we were both greedy players. We only cared about ourselves. But what if people assign different values to different outcomes? What if the matrix is no longer symmetrical? How would we deal with that? Okay, so in the previous one, we had B minus is kind of neutral. If I get an A and you get a C, payoff for me is good. I don't care about you, so that's a big win. But maybe now, let's say like the other person is my brother or my mother or something like that, and we care about their outcome as well. So AC was 3, right? Because I only cared about my A. But maybe that's now -1, because I don't want any bad outcome for the other player. And now maybe CA, I get a C and they get an A. It was -1, but now it's a -3. It hurts because the person I care about did better than me and they kind of threw me under the bus, right? So I'm kind of angry at that. So maybe this is more emotional or illogical or whatever, I don't know. But this is all contrived in order to make up some different numbers, right? So in this example, if both of the players are caring, right? In this example, both players are greedy and assign higher payoffs to their own grade. They don't factor what happens to the other player at all. But like I just said, what happens if the other players care about each other? So maybe this 3 becomes a -1 because of some guilt. Maybe -1 becomes -3 because of some anger or whatever. Oh, oops. So let's look to see if there's a dominated strategy. Nobody saw that. So if the partner chooses alpha, okay? If I choose alpha, I get 0. If I choose beta, I get -3. So alpha's better if they choose alpha. If they choose better, I get -1. If I choose beta, I get 1. Okay, so beta is better in the second case. So nothing is strictly dominated in that case. There's no dominated strategy. So maybe if there's no dominated strategy, okay, now we're in that sort of gray area where it's like maybe I choose which action could get me the best possible outcome, right? Or which action I'm trying to avoid the worst possible outcome, something like this. Or maybe like someone said before, I want the average of the two or whatever, okay? So if there's no dominated strategy, well, what can you do? You've got to choose something. So let's have another look at mixed players. So if one is greedy and one is caring. Will the choice be different if we know the strategy and payoffs of the other player are actually different than ours? Well, let's have a look. So this was for the greedy players. This was for the caring players. And so what we're going to do is we're going to take me as the greedy player and the partner as the caring player. So we combine the first half of the first matrix and the second half of the second matrix into a single matrix that's no longer symmetrical. Okay? So as the greedy player, is there a dominated strategy in this game? Okay, let's do the algorithm again. And by the way, if in any of my lectures ever I'm doing an algorithm this much, you better believe it's going to be on an exam. Okay, so solving this sort of thing on an exam is definitely going to be there. Is there a dominated strategy in this game? Okay, let's look. Can anyone tell me so I don't have to? Has anyone been moving? Oh, nobody did it yet. Okay, if they choose alpha, my alpha is 0, my beta is -1. So alpha's better. If they choose beta, my alpha's 3, my beta is -1. So alpha dominates beta, strictly dominates beta. It's always better. Let's flip it now. So instead of being the greedy person, I'm the caring person. So here's the payoff matrix for me. As the caring player, which strategy do we choose? Well, let's just look. If there's a dominated strategy, I don't play that one. So for the greedy player, I'm going to choose alpha, or sorry, if the greedy player chooses alpha, then alpha is better. If the greedy player chooses beta, however, then beta is better. So there is no dominated strategy. So what do we choose here? Well, this is a situation where we do have some other information that we should consider because this is no longer a symmetric matrix, right? So before, it was symmetric, meaning that if there's no dominated strategy for me, then there's no dominated strategy for the other player either. But let's have a look from the point of view of the greedy player, which we just did, in which case alpha dominates beta for the greedy player. So if we assume that the other player is rational, we know that they will choose alpha because it's strictly better than choosing beta in all possible cases. And so if we know they are going to choose alpha because that's their strategy that dominates beta, then we're going to look at, okay, fix their alpha, we are going to choose alpha because it's the best response to their chosen strategy. So the best response to greedy choosing alpha is caring choosing alpha. And so the moral of the story here is like putting yourself into someone else's shoes so that you figure out what they will do and then try and do that, okay? So a best response, let's look at that a little bit more. The strategy which performs best against a given other strategy is called a best response. In that example, we knew that the other player had a best choice, so we choose our best response to what we know they should do if they're a rational player. And so, oh, this is the quote I was looking for. To know your enemy, you must become your enemy, right? It's not always enemy. It could be to know your partner, you should become your partner, right? Like it's, yeah, important advice. So what makes a game then? Let's define the game mathematically. So in any game, we have a number of players. I, J, K, L, S, T, U, 1, 2, 3, doesn't really matter. We have players I and j in this case. This here is actually describing the numbers game that we played at the beginning. So I want a mathematical definition of the numbers game. So the players I, j, k, everyone here, if we had more letters, everyone would get a letter. A strategy, S sub I, is the particular strategy of player I, meaning that is the choice that player I made. So if you chose 13, you chose 71, whatever, that is the strategy S sub I, okay? And if you were player Q, S sub Q would be the thing that you chose. Capital S sub I is the set of all strategies for player I, meaning it is the set of all things that you could have done, right? So for this game, that's symmetric. So everybody in the class got to choose the same thing. But we can think of games where, you know, one person has a different choice than another person. Maybe one person has a sword and one person has a gun or something like that. I don't know. And so in this case, that was the numbers 1 through 100 that you could choose. S, the strategy profile. A strategy profile, here I said sheets, but because the last time I played this, I actually had people write it down and then I counted them up and it took way too long. So that's why I switched to the online thing. But a choice for everyone. So you all, or the 40 of you who responded, the spreadsheet that I have that lists everyone's choice, that's called a strategy profile. It is a playing of the game in which everyone chose something. And then S minus I would be a strategy profile for everyone but player I. And the reason I'm doing all this is because we're going to use these in a second. And the payoff UI of S, that is the utility or the payoff, so the utility for player I given a strategy profile. So that is the outcome for you, player I, given that everyone else chose all of these things, okay? And I joked around last time about giving someone $5 if they were the winner, but yeah. And we assume all of these are known values because we have to write them in a matrix to solve this game, right? If you're playing an incomplete information game, you don't know all the rules, you don't know all the outcomes, then that's bad. You don't want to play those games necessarily. All right, here's another example game where it is no longer symmetric and the strategy sets of the players are now different. So, I don't know, let's take some sort of, I always struggle to come up with an analogy for this. Maybe it's like a soccer penalty shootout or two players fighting or something like that. But essentially, player 2 has the choices of left, center, or right. Player 1 has the choices of top or bottom. Just arbitrary things. And here's the payoff matrix for that. I'm not going to go into what this means, just arbitrary numbers that we can do math with. So we have players 1 and player 2. The strategy sets are S1, those are the strategies that player 1 can play, so it's top or bottom. S2 is left, center, or right, so that's what player 2 can play. And the payoffs are this matrix. But for example, if I were to ask you, what is U1 of TC? Well, that means what is the utility for player 1 if player 1 chooses top and player 2 chooses left? Oh, sorry, player 2 chooses center. And so that's right here. So that's 11. Okay? Also, what is the utility of player 2 if player 1 chooses bottom and player 2 chooses left? Well, that's right here because it's the second one. That's the utility of player 2. So that's what this means in mathematical terms. That's how you define all of these things. So let's do the same thing that we did before. All right, take a few seconds, have a look at this, and someone put their hand up when they haven't answered. Does player 1 have a dominated strategy? Oh, I need hands. I'm going to choose someone I haven't chosen yet. Yep.
I'd say the top would be the dominated strategy based on player 1.
Okay, so let's just have a look. So there's a chance, because we've been doing these from the left-hand side, there's a chance that you got your calculations backwards, because now we're looking at, does player 1 have a dominated strategy? Okay, so let's see here. Oh no, that's the next thing I'm going to do. Don't worry about that. So let's just look at everything that player 1 or player 2 could do. So if player 2 chooses left, then B is best, right? If player 2 chooses C, then T is best. If player 2 chooses R, then B is best. So nothing is always better given everything that player 2 could do. So no, player 2 doesn't have a dominated strategy in this case. Does player 2 have a dominated strategy? Oh, sorry. So player 1 doesn't have a dominated strategy. Sorry. Yeah, that's player 1 does not have a dominated strategy. Does player 2 have a dominated strategy? Yep.
Yes, it does. The rightmost strategy is dominated since the center strategy always does better for player 2.
Okay, so that's a good answer. So let's calculate that. Okay, so over here we can see that if player 1 chooses T, because we're talking about player 2 now, we have to do it from the opposite side. So if player 1 chooses T, L will give me -1, C will give me 3, R will give me 0. If player 2 chooses B, L will give me 4, C will give me 2, R will give me 0. So there's no, in the case of T, C is the best. In the case of B, L is the best. So you might say, no, there's no dominated strategy, because our brains are looking for, is there a single best thing, right? But that's not what domination is. What domination is, as you said, is that is there a strategy that another strategy always does better than? And in this case, yes. If we choose top for player 1, then C does better than R. If we choose bottom for player 1, then C does better than R. So if I was to ask this on an exam, then you would say, yes, C dominates R, or whatever the answer might happen to be for that particular matrix. So strictly dominated, if we want to now put this into more mathematical terms instead of just an English definition, player I's strategy, SI prime, is strictly dominated by player I's strategy SI. So we have two strategies here, two choices, SI and SI prime. If the utility or the payoff for player I, given SI and all the other choices, is greater than, strictly greater than, the utility of choosing the other thing for all possible choices of all other players. Now, why am I saying S minus 1? Because there could be more than 2 players in this game, but it is very difficult to draw 3D matrices or more dimensional matrices on a slide. Okay, just realize that when you actually do this in practice, there could be a bunch of players. So we have to talk about everyone else's choices, not just that other person's choices. So that's why we phrase it like this. And on an exam, I'm going to give you 2D matrices. So don't worry about harder things. Here's another game. Defense. So this is a little bit warlike. Hopefully you never have to defend a city, but if you do, maybe you can think back to this lecture, okay? You're a general defending a city. Is anyone here a general? Yeah, we got a couple generals. All right, so pay attention. You have an army. You're in a city. An attacker has 2 armies. There are 2 paths leading to the city. I'm going to draw a diagram of this in a second. There's the easy path. It's just fields of flowers, right? It's really easy for the army to march along that path. Then there's the hard path. You have to go through, I don't know, over Mount Everest or something, right? It's a hard path to get through. As the city defender, you don't know where they are coming from, and you have no ability to scout them until they show up. That's the contrived example that I'm working with. But you have to choose. Do I put my defensive army at the easy door or at the hard door? Okay. Here's the rules. If the attacker chooses the hard path, they lose an army because it just dies on the way there, right? It's really hard to get, there's no food, it's all snowy, their elephants die or whatever they're come over the mountains with. But if your armies meet, the attacker loses an army as well because you chose correctly. So if your armies meet, then you both lose an army, okay? The enemy wants to maximize the number of armies that they get into your city. Obviously, they're trying to take over this city. So let's have a look. This is what it is, right? There's this easy path, there's a hard path. Where do you put your army? You can only put them in one place. right? And we're defining this game. Yes, this is not an actual wartime scenario. You'd send out scouts, you'd know in advance, maybe you could split them up or whatever. But let's have a look at the payoffs of this, okay? So we are assigning linear payoffs to the number of armies and what we want to do. So as the attacker, the payoffs are the number of armies that reach the city. So let's look at the attacker. Oh, and also the defender's payoff is the number of attacking armies that are killed, because, you know, the number of attacking armies that are killed are the ones that don't reach the city. So does defense have a dominated strategy? Let's look again. Let's look at attacker. If they choose the easy path, then defense is going to get a 1 here, because they are going to kill one of the armies if they both meet at the same location. But if attacker chooses, easy, and defense chooses incorrectly, they choose hard, then they kill 0 of the armies, and that's kind of bad. If the attacker had chosen hard, so in this case, if they choose easy, our best choice is easy, right? If the attacker chooses hard, then if we choose easy as the defender, we kill 1 army because we've chosen incorrectly, but one of their armies died on the way. Okay, so that's still just a 1. But if we also choose hard, then both of the attacker's army get defeated. So does defense have a dominated strategy? Well, in the first case, easy was better. In the second case, harder was better. So no, easy does not have a dominated strategy. But let's listen to Sun Tzu. Does the attacker have a dominated strategy, right? So, okay, let's go over here. If defense chooses easy, if the attacker chooses easy, they score a 1 because they get 2 armies to the city, but then the defenders kill one of them. So one of them reaches the city. If the attacker chooses easy and we choose hard, we still get a 1. Even though they didn't defend us, we lost 1 on the way, right? Okay, so the easy is, for easy, it doesn't matter what we do. But if the defense chooses hard, if we choose easy, then we get both of our armies in the city. But if we choose hard, well, we lost 1 on the way and we're going to lose 1. So we don't get any into the city. So in this case, in the easy case, they're both the same. But in the hard case, choosing easy is better. So easy weakly dominates hard because it's not always strictly better, but it always does at least as good. Okay? So weakly dominated strategy, and what does this tell us? Well, we probably shouldn't play weakly dominated strategies, right? But if they're all the same, then we got to choose one of them. So weak domination is that, if they're all the same, then they're equal. They're not weakly dominated. So weakly dominated essentially just means that for everything, we are at least as good as it. But for one thing, at least one thing, we are greater than it. Okay? So this strategy does better in at least one case and equal to or better in all the other cases. That is weak domination. So you probably shouldn't play a weakly dominated strategy. Therefore, if you know the attacker has a weakly dominated strategy, which is the hard strategy, that means they're probably going to take easy. So you should defend the easy road because you know what your attacker will do. Okay, so quick recap, because that's a lot of information. Games have player strategies and payoffs. We want to maximize our payoff. A strategy dominates another one if it's always better, strict, or as good, weakly dominated, to choose it. Never choose a dominated strategy. And if there is no overall best strategy to play, consider the other best choices first. And if they do have a best choice, pick a best response to that best choice. Okay, so that's what game theory tells us so far. Now, let's have a look back at the numbers game. Why is this? That's not on my screen, but I want to, oh, this better not. Okay, if that made me have to like redo everything. Okay, so here was our numbers game. Those are the things that we chose. 2/3 of the average was 21. We had a couple of people who were very close to 21. Are there dominated strategies in the numbers game? Can anyone tell me? There we go, right in the back. Okay, So what is the reason for that? Yes, but we need something a bit stronger than that. Nothing will ever be 2/3 of the average if everyone picks it, right? But what did you mean by that? Just go through the chain of thought there. Yes, you're almost there. So, what would dominate that strategy then? There you go. Okay, so let's just have a look. If everyone chooses the maximum value of 100, let's try and figure out the highest number that could be 2/3 of the average. And we'll just round it to integers for simplicity. So if everyone chooses 100, then the average is going to be 100. So 2/3 of that average is going to be 67, right? So what does better than 100? Everything between 68 up to 100, right? Actually, I shouldn't have this bracket here. It should be up to 99 because 100 doesn't dominate 100. So everything, not only that, apologies, I read this a little bit incorrectly, but not only is 100 dominated by everything between 68 and 100, but everything between 68 and 100 is dominated by 67, right? So if anyone in the class chooses higher than 67, anyone else who chose 67 will, by definition, do better than that person, no matter what everyone else chose, right? See how that works? So if in the worst case, the average is 67. And so if we choose, the 2/3 of the average is 67. So anyone who chooses higher than that is going to be further away than the real 2/3 of the average than anyone who chose 67. Okay. But can we keep going? Please don't just yell out answers. I know the answer. Just put up your hand if you want to answer something. Thank you. If no one plays a dominated strategy, what does that mean? Well, if no one plays a dominated strategy, and we know that 68 through 100 are dominated by 67, it means now really the only logical choices is 1 through 67, right? So those are the only things that we're going to choose. But let's apply the same logic. If everyone chooses the max of the non-dominated strategies, the average is now 67, so 2/3 of the average is 45, and so 46 to 67 become dominated by 45 in that case. And we can just keep applying this recursively all the way down to 1 if we want to, right? Now, I've played this game a lot of times in a lot of different courses, and you might think that the correct answer, therefore, is 1. But picking 1 will never win you that game. Because it's sort of this game, if I know that they know, or if I know that they're rational, oh crap, but if they know that I'm rational, but if I know that they know that I'm rational, but if I know that they know that I'm not, like, it just goes back and forth, and how far do you stop, right? And so if you keep playing this game over and over and over with a class of people, you will see that number slowly go down and down, and I think I played it like 3 times one year in a class, and it got down to like 10 or something like that. And I had to take out the trolls because people were like just picking 69 all the time, stuff like this. But like if people are actually caring, then usually it does tend to go like sub 10. But the thing is, there's this weird thing where it's like, I don't trust that the rest of the class understands this. Therefore, it's probably going to, some people be choosing in the 20s, therefore maybe I should choose like 5, but then if I choose 5, that actually bumps the average up, so maybe I should choose 8. Like, it's this weird mind explosion of logic in how you actually make these choices. So this is called a rationality chain. So this is, if you're being rational, these are the dominated strategies. These are the dominated strategies if you're rational and you know the other people are, and so on and so forth, right? I know that you know that I know, blah, 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 blah. Okay. So I'll just leave that there because there's no real answer to that, right? What's the best choice? Because that depends on the group of people who are playing. But we did talk about best responses, and I want to introduce one other concept before we finish today's class. And so remember, a best response is if I fix a strategy of the other player, the best response is my strategy that does best against that particular thing. So let's talk about the idea of a Nash equilibrium. So a Nash equilibrium is a strategy profile, okay? Meaning it's a choice for everyone in the game. A Nash equilibrium is not me choosing alpha. A Nash equilibrium is a choice for everybody, right? It has to be everyone making a choice. So if everyone makes a choice, it is a Nash equilibrium if for each player, their choice is a best response to each of the other players' choices. Okay? So if each player is best responding to each other player, then that is a Nash equilibrium. What is a motivation for a Nash equilibrium? First, there's no regrets. So this means if we hold the strategies of everyone else fixed, so if I've made a choice and you've all made a choice, and this happens to be a Nash equilibrium, we're best responding to everyone. No individual player has any incentive to have chosen something else. Because if you are best responding to everyone else's choice, why would you change your strategy? The best response does at least as good or better than any other choice. So there are no regrets in a Nash equilibrium. The next is that it is self-fulfilling, meaning that if everybody is rational, of course, and they know about this concept, if everyone believes that everyone else is going to play a Nash equilibrium, then they probably will as well. Why? Because we are all best responding to each other. All right. Wouldn't be a lecture if I didn't show you a calculation. Here is how you calculate the Nash equilibrium. So we have like left, center, right, up, middle, down, whatever these actions are don't really matter. It's just the numbers that matter. So what is the best response of player 1 to player 2 choosing L? That's a great exam question. It's pretty easy, right? So here, again, please don't just say the answers. It's a little distracting. So I'm going to go through it. So if they choose L, my up gives me 0, mid gives me 4, down gives me 3. Therefore, I'm just going to mark that my best response as player 1 to player 2's L was M. Okay, so I've just colored that in red. What is the best response to C? Well, I'm not going to go through all of those individual calculations again, but that would be U. My best response to R would be D, because that's where the highest value is. Now, what we do is we calculate all the best responses for the other player as well. So we have to go across. What is the best response for player 2 to me, or player 1 choosing up? Now we have to look at the second numbers, okay? So L would give me 4, C would give me 0, R would give me 3. The best response is L. What is the best response to M? Well, that would be C. I know the green font is a little bit hard to read. The best response to D would be R, okay? So the question is there a Nash equilibrium for this game? And if there's 3 outcomes. There's either no Nash equilibrium, that can happen. There's one Nash equilibrium, or there are multiple Nash equilibria, okay? So on an exam, I would give you a matrix and I would ask you some of these types of questions. So what we do here, on an exam, if I gave you this question, just circle where the best responses are. And then if you want to know if there's a Nash equilibria, you just look for any cell where everything is circled. And then that would be a Nash equilibria, okay? So right here, the Nash equilibria would be, now it's not down, it's not right, the Nash equilibria is player 1 choosing down and player 2 choosing right. It's not a single action, it's a selection for everybody. And let's just have a look at that. Are there no regrets? That's correct, because, okay, player 1 has chosen down, player 2 has chosen right. For player 2, does player 2 have any regrets? Well, we know that does player 1 have any regrets? We know that player 2 has chosen right. And we know that we are choosing the best response to write. So anything else would be equal or less than this one. So player 1 has no regrets, but player 2 is in the same situation. They know what player 1 is doing and they've best responded to it. So in this case, there are no regrets for either player. Now, no regrets does not mean that it is necessarily the best outcome for both players. There may be a separate choice for each player where they both get more. Or one player gets more and one player gets less. It doesn't mean it gives you the highest value. It just means that no player has any regrets with this choice. Let's do one more example. Okay, best response to L, 11. Best response to C, 3. Best response to R, 8. Now we're going for player 2. Best response to up. Oh look, we actually have 2 here because C and R both have the same value. There can be multiple best responses, so make sure that you're looking for multiple best responses. Best response to M is 2. Best response to D is 7. Okay, what's the Nash Equilibria? Hand up. I'm not choosing you out of spite. Are there any Nash Equilibria? Someone else. No, come on. I know the answer. I'm trying to get class participation. Have you answered yet? No, you haven't. Okay. There you go. There are 2 Nash Equilibria in this one. So you would put both of them down. Okay. So yeah, I'm just trying to, I know the answer. I've got a slide coming up with the answer. So I'm just trying to get different people to get off their cell phone or something like that. So what is the relation of Nash Equilibria to dominance? Well, in this one, alpha strictly dominated beta. So let's find the Nash Equilibria, if there is one. So let's look at alpha, 0 is the best, beta, 3 is the best. For the other one, for alpha, alpha is the best. For beta, 3, or beta is the best. So if alpha strictly dominates beta, we can say that in a Nash Equilibria, no strictly dominated strategy can ever be played in a Nash Equilibria. Okay, so that's a good result. We know that if we are in a Nash Equilibria, then our strategy, there's no better choice. It can't be strictly dominated by everything. However, there can be more than one Nash Equilibria in a game, right? So if there are 2 Nash Equilibria, like this is trivial to calculate, there's one up here at alpha alpha. There's one here, beta beta. But this one is obviously a better outcome for both players, right? So that would be the one that you would want to choose. But weakly dominated strategies can be chosen, okay? So that's just something to watch out for. A weakly dominated strategy, which for player 1 here would be beta, can be chosen in a Nash Equilibrium. So in a Nash Equilibria, no player can do strictly better by changing their strategy, okay? Let's look at another game. This is called the investment game. So let's just say we are all playing in this investment game, and I'll say why it's the investment game in a bit. But the choice is you choose to invest $100 or you choose not to invest anything, okay? Here are the payoffs. If you chose not to invest, then you gain or lose nothing, right? If I don't put any money into the stock market, I don't get any money back, but I don't lose money either. However, if you chose to invest, if greater than 80% of the people invested, you're going to double your money. But if less than 80% of people invest, you're going to lose that money, right? So this is an interesting game. And the interesting part of this game comes when I put it on an exam, okay? And instead of money, it's bonus marks. But instead of gaining or losing nothing, if you don't invest, so you can actually lose marks on this question because you're investing, and it's like 1 or 2%. It's not a big thing, but you're investing 1 or 2%. And what the interesting thing is that it all hinges around this percentage. So if I ask this on an exam, do you choose to invest 2% in this question? If that number is 10%, then obviously everyone thinks, yeah, more than 10% of people are going to choose this. So everyone would put down choose to invest. But if that number is 90%, do I think 90% of people are going to gamble with their grades? Maybe not. And so now those people maybe don't invest. And so I have found a nice little sweet spot for that over the years. And so maybe you'll see this as a bonus question on the exam. But the interesting thing is that no matter how many times I get up here and give this lecture and tell you, just choose to invest because if everyone does, you all get free bonus marks, there's a bunch of people who don't because they don't trust it, right? And that's one of the interesting things about choices in life is that they depend on other people. So let's have a look at the investment game, Nash Equilibria. Hand up, please. What is, or is there, a Nash Equilibria for the investment game? Please, I know the answer, someone different. I just want to hear from different people. You covered it up with the head scratch there, that was good. Someone from over here. You're not going to be shamed. I'm not going to say your name on YouTube, don't worry about it. Okay, Yankees hat. Do you think there's a Nash Equilibria for this game? So what could everyone do? What's a choice for everybody that might be a Nash Equilibria? Or if you don't think there is one, then just say that you don't think there is one. Yep. But we need a choice for everybody. So assign choices to everybody. And is that a Nash Equilibria? Okay. Anyone else think there is one? Oh, very back, someone new. Okay. So in terms of regrets, why would that be a Nash Equilibria? There you go. So you were on the right track. You just needed like an assignment to everybody, right? So there are two Nash Equilibria for this game. Everybody invests or nobody invests. Why is that? If everybody invests, if any of those people change their strategy to not investing, will they do better or worse? Worse, right? I hear a bunch of people whispering it. So if nobody invests, then nobody's winning any money. But if any single person chose to invest and everyone else stays the same, then they will do worse, right? And so those are the Nash Equilibria for this game. Now, I want you to think about Nash Equilibria for the numbers game. I'm not going to put that one on the screen. Just think about that one because that could be a cool question possibly for an exam. But I do have some things here. Possible exam questions. Given a payoff matrix, compute the dominated or dominating strategies. I'll be asking which strategy dominates which other strategy. Explain why a choice of strategy is good or bad for a given matrix. Compute the best response to a given strategy. Construct a matrix such that one strategy dominates another strategy. I think that's an interesting question. I'll give you a blank matrix, get you to put some numbers in. Definition of Nash Equilibrium, both the mathematical definition and the English sort of descriptive definition. Also, calculate the Nash Equilibrium for a matrix, and there may be none, one, or multiple Nash Equilibria, or I will describe a game to you, and you give me the Nash Equilibrium for that game.